In this video, we will look at a few problems on the first law of thermodynamics. In particular, we shall use the PV graph or PV diagram in the calculations of change in internal energy, heat, and work done by the system or on the system. Problem 1. The figure below shows a cyclic process, one in which the initial and final states are the same. So it starts at A and proceeds counterclockwise to point B and then back to A. The total work done is negative 550 joules. Now note the negative sign there. Find the change in internal energy and the heat added during this process. So let's do the change in internal energy first. Now the change in internal energy is the internal energy of the final state minus the internal energy of the initial state. In this case, the final state is state A, so UA, and the initial state is also state A, so UA, which is 0 joules. Now using the first law of thermodynamics, which states the heat added equals the work plus the change in the internal energy. The internal energy change has been shown to be 0 joules right there. So that means the heat added during this cyclic process is the same as the work done. And in this case, the work done is minus 550 joules. So that must also be the heat added during this process. And that solves the problem. Problem 2. A gas in a cylinder is cooled and compressed at a constant pressure of 2 times 10 to the power minus 5 Pascal. The compression is from 1.2 cubic meter to 0.8 cubic meter. A quantity of heat of magnitude 2.5 times 10 to the power 5 joules is removed from the gas. Now find the work done by the gas and also the change in the internal energy of the gas. Note, the work done is work done at constant pressure. So it is quite simply the pressure times the change in volume. Now the pressure is 2 times 10 to the power 5 Pascal. And the change in volume is from 1.2 to 0.8. So it is 0.8 minus 1.2 cubic meter. And that's going to give you minus 80,000 joules for the work done. Note that this minus sign for the work is compatible with the compression. For part B, we want to determine the change in internal energy. So again, using the first law of thermodynamics, heat into out of the system equals the change in internal energy plus the work done. Now note that this much heat is removed from the gas. So that means that number has to be negative. So the heat removed corresponds to the value of minus 2.5 times 10 to the power 5 joules. Internal energy is what you want to determine. The work is minus 80,000 joules that we have determined in part A. And now we can solve for the change in internal energy. And that's going to give you minus 1.7 times 10 to the power 5 joules. And that solves the problem. Problem 3. Figure below shows a closed cycle for a gas. So this is a PV diagram or graph. Note the change in internal energy along CA is minus 150 joules. So CA, the change in internal energy is minus 150 joules. The energy transferred to the gas as heat is 180 joules along path AB. So here is 180 joules. 50 joules along BC. So the heat is 50 joules along BC. How much work is done by the gas along path ABC and also along path AB. So let's apply the first law of thermodynamics to the path ABC in that order. So we know that Q, or heat added for ABC, equals the change in internal energy for ABC plus the work done for that ABC. Now we do know that the heat added for ABC is quite simply 180 joules plus 50 joules. So 180 plus 50, and that's going to be 230 joules, because 180 is from A to B and 50 is from B to C, so you just sum them up. Another thing that we do know is the change in internal energy from A to C. Now, because internal energy depends on the state, so the change in internal energy from A to C must be the negative of change of internal energy from C to A, which we know to be minus 150 joules. So therefore, the change in internal energy from A to C is 150 joules. Right there. Note that the change of internal energy from A to C must be the same as the change of internal energy ABC in this line, because the path does not matter. What matters is the initial point and the final point when it comes to the calculation of the change in internal energy. So substituting 230 joules for QABC and 150 joules for the change in internal energy of ABC, we can calculate the work done by the gas along the path ABC, which will turn out to be 230 joules minus 150 joules, that is 80 joules. Now what about the work done by the gas along path AB? Now since ABC is made up of AB plus BC, so the work along ABC equals the work along AB plus the work along BC. However, BC is a constant volume process. That means the work for BC is 0. So that means the work along AB must be the same as the work along ABC, which we have computed, and that is 80 joules. And that solves the problem. Figure below shows a closed cycle for a gas, the change in internal energy of the gas as it moves from A to C along path ABC is minus 200 joules. So the change in internal energy as it goes from ABC is minus 200 joules from A to C via point B. We are also told that as it moves from a C to D, as the process takes place from point C to D, 185 joules must be transferred to it as heat. So the amount of heat that is transferred to the sample from C to D is 185 joules. An additional transfer of 90 joules to it as heat is needed as it moves from D to A. So from D to A, the sample receives an additional 90 joules of heat. Now since heat is being pumped into the system, the signs are positive and positive. We want to determine the work that is done on the gas as it moves from C to D. So let's write down the first law of thermodynamics for CDA, like that. It simply becomes Q CDA equals the change in internal energy for CDA plus the work done along CDA. Note that the heat added for the process CDA is quite simply the heat added along CD plus the heat added along DA. So that's going to be 230 275 joules. The change in internal energy for this process is the internal energy at point A minus the internal energy at point C. Now we are given the internal energy change for process A, B, C. That means we know that the internal energy of C minus the internal energy at A is minus 200 joules. So the internal energy of A minus the internal energy at point C is quite simply minus 200 joules, which is positive 200 joules. So we know that as well. And we can compute the work done along CDA. So from this result, we immediately see the work along CDA is quite simply 75 joules. Note, CDA is made up of CD and dA, but dA is a constant volume process, so the 75 joules must also be the work done on the gas as it moves from C to D, and that solves the problem. Problem 5. Figure below displays a closed cycle for a gas. From C to B, 45 joules of heat is transferred from the gas. So that means QCB must assume a negative value, so it's minus 45 joules. Now from B to A, 120 joules is transferred again from the gas's heat. So QBA must also assume a negative sign because heat is being pumped out of the system. Magnitude of work done by the gas from B to A is 70 joules. Now note, B to A involves contraction or decrease in volume. So the work from B to A must be negative 70 joules. And finally, from A to C, 380 joules is transferred to the gas's heat. So QAC is positive 380 joules. We want to calculate the work done by the gas from A to C. Right there. So we shall apply the first law of thermodynamics to this process that begins at point C, goes to B, then A, and comes back to C. So this is a cyclic process. Since it comes back to the original point, the change in internal energy is quite simply UC minus UC, which is 0 joules. The net heat transferred during this cyclic process is quite simply the heat transferred out of the gas, which is minus 45, plus the heat transferred out of the gas from B to A, that is minus 120, and heat that goes into the gas, which is plus 380. So when you add all these contributions, you get the net heat for that cyclic process. That is the net heat transferred to the system during that cyclic process, 250 joules. Now all we have to determine is the work for the cyclic process, the work done for the process C, B, A, C. Now from C to B, the process is a constant volume process, so there is no work done. Now from B to A, we know it's contraction, and it's given minus 70 joules, that one, followed by the final contribution, work done from A to C, which is what we want to determine. So writing first law of thermodynamics for the cyclic process, the heat is 215 joules. The change in internal energy is 0, and the work done is minus 70 plus the work done by the gas from A to C, which now you can solve to be 285 joules. And that solves the problem. Thanks for watching.